Hello, anyone want to join me? I'm just about to live stream. I've started. We'll give it a few minutes, and then we'll keep on going. Minutes. Don't want the echo. I think one of my primary viewers is not awake anymore. Okay. "16 frames per second. It's not good frame rate whatsoever. Let's see if we increase this to 2 hours per second if it throws everything out of loop, out of whack. These orbits seem to oscillate a lot more. Well, I don't know if anybody is going to show up. Well, let's get going on this. I will go ahead and start on Kintage. We have this moon system that is slightly, not just slightly, it's very much angled. This is not Sitse, and over here is Kintage. We need to edit the base file and save it for right now. Oh, my Chromebook went sleepy bye. Alright, let's pull up Kintage, satellites. And how many satellites do we have? We have the main moons, which are 8, and we need to create a bunch of minor moons. 10 to begin with. Yeah, let's do random moon. Are they too big? Yeah, that's too big. Random small moon is probably too the right size or not. You know what? We need to add 10 and we'll care about changing the size and changing the names. 4, 5, 6, 7, 8, 9, 10. And we're saving this under test simulation. And you have to save and reload to really edit the orbits. That's the reason why after you're adding things, it's best to just save it then. Now these look all nice and orderly. Now we're going to mess everything up. So let's go ahead and rename these to our numbering system. And don't worry, it doesn't matter what texture they are. All of these are going to become so small they might as well just be potatoes. That's a hyperbole right there. And Kintage C1, and we have 10 of these. But all of them will be C1 0 blank or 1 0. This one is 101. Yeah, we'll just accidentally copied the whole thing. Want to copy just that part. And this will help me keep organized. That's one of the key things when you're making the system. You don't want to get lost in what you've added and what you still need to add. And look what I just did. Accidentally added 2 102s. This should be 103. Then this should be 104. No, not C10, C104. 105. 106. 107. 108. And 109. Lastly, 110. Okay. So now we have all of these named. Just to make sure we don't lose anything in the middle of building this minor moon system. Test. Yes, we want to replace our test file. And now it's time for me to pull up my Chromebook and get some figures pulled off of Google Docs, Google Sheets. Okay, so what do we want to do first? Well, we want to adjust the mass, and I have on my handy dandy spreadsheet mass of Earth, mass in terms of Earth for each of these. And then, once we have the mass inputted, we can adjust the density to get these to the right size. No, not that. So the mass in terms of Earth, 6390. I'm going to round these myself because I believe if I'm correct on this, it's going to cut me off. 897, yeah, it's going to round to 4 digits, 4 significant digits. Okay, so that is our size, and now this density has to be changed to match 3.27. Oh, I'm looking at the wrong... I'm looking at major planet, major moons instead of minor moons. My fault. Okay, this is a lot less. Okay, I need to count how many decimal places we really have here. 1, 2, 3, 4, 5, 6. Is there a way to scientific notation? Let's select all of these in my Google Docs. Sorry, guys. Make it all scientific notation. There, that's easier on me. But at the same time, we want more significant figures. Okay, significant digits. So now I have it set up on my end so that you guys don't have to wait for me. 3.4813 times 10 to the negative 9. And now, what happened? I messed something up. 3.48131 10 to the negative 9. Now we're good. Okay, so we want to get this down really low. We need to have it down to 1.8 grams per cubic centimeter. Add a little bit more iron. Take away a little bit of silicon, and there we go. That one's perfect. Golden, golden. Okay, now that that one is out of the way, we're just worrying about the size and composition, mass and composition of these minor moons right now. We'll go back through, or I'll go back through, and change the orbital characteristics after we settle this. Okay, this is similar in mass. So this one is 3.4982 times 10 to the negative 9. Basically the same exact mass. A little bit higher density. We can be at 1.93 for this. Oh, that was almost perfect. What would be best to take away? That was too much. Add. Take away a little bit of silicon, and there we go. Golden 1.93. So that's now the perfect size. Move on to the next one. And Earth. So the goal here is I went through and calculated an appropriate radius that I was going to aim for these. And I'm doing radii between 10 and 19 kilometers for each of these. And after I figured out that radius, I used it to figure out, I determined an appropriate density for these moons. And once you have a radius and a density, you just crunch some numbers and you can figure out what the mass needs to be for moons that are basically dirty snowballs. That's what all of these are going to be, are dirty snowballs. These are minor moons. So 1.8142. I think it would cut off before that, so I don't need to input any more digits than that for the mass of this small one. And this is 1.87 grams per cubic centimeter. So let's see. Took away a little bit too much. We're right in that area. Okay, that's perfect. Now it's on to the next one. Bye. So on to the next one, we have a C4. And this one will be 2.067 times 10 to the negative 8, not 9. So it's a little bit bigger than the others by a factor of 10. but still, it's only 16.9 kilometers across. And this one is a little bit denser. It's 2.25. Still quite a bit of water in there. Okay, let's get it really close, add some silicon. Stop going up and down at the same time. There we go. That's the perfect amount. And now on to the next one, which is going to be C5. And C5 is Earth masses 3.07. 859. Still really small. That's not the right. So it's going to be somewhere around 10 kilometers. We need to get it to 1.89. Okay, we kind of overshot it. Okay, now we're under. Add a little bit of silicon in. Ooh, too much silicon. We're going to have to add silicon and then take away a little, or add a little bit of water, I mean. Add a little bit of silicon. Add a little bit of iron instead, and there we go. That's the 3.2 kilometers is the radius. That's what it should be. Now we're on to our next one. That texture, I don't recognize it. Oh well, it's not going to stay around for long. Let's see, what's the next one on my handy dandy spreadsheet? This is another one of the ones on the larger side of these potato-shaped moons. Not potato size, but they are potato-shaped. .88. That's what this one needs to be in density. And add back a little bit of silicon after we've added water. Take a little bit of iron. And there we go. Just gotta mess with the little sliding bars to get it right perfect. So I didn't add as many as I should have. So I'm going to have to go back and add a few more of these planets because I was looking at the wrong area of my spreadsheet. And that is fine. This one has a mass. That's another one on the larger side. Times e to the or times 10 to the negative 8. There we go. That's a big hunk of iron. And we need to reduce this down to the size, or to the density of 2.14. Take away a lot more iron so that there's more silicon. What am I doing? You need to watch what you're doing, Ty. Mal, what are you doing, Mal? Okay, there we go. Which one are we up to? The 8th? Let's go ahead and adjust to move through my spreadsheet. Here we go. This one is at 1.17795 times 10 to the negative 8. And we need to get this one down to 1.92. Oh, I just slid over it, and there we go. That one was an easier one. 109. Okay. So this one is now back to a smaller, not really small, but still a smaller size. Times 10 to the negative 9. I must have hit something wrong. 5.47559 e to the negative 9. There we go. .88. There we go, perfect. And finally, we are to 110. The last one which I added. I'm going to have to save this after I add a few more. By a few, I mean 8 more. Yeah, timeout can't count. 3.88428 times 10 to the negative 9. This one needs to be about 2.28. No, 2.03. Kind of overshot the mark there. 2.03. There we go. All right, let me go ahead and add 8 more. we'll add them as small moons. 1, 2, 3, 4, 5, 6, 7, 8. We'll save it and reload again. These weren't supposed to be added like that. I'm gonna have to correct that mistake there. I'm gonna have to delete 3 of them. Okay, what's happening here? Okay, now that I deleted them, let's save, or let's reload. I saved, and now I'm reloading. I don't know what happened there. It was acting all strange. Random small moon, there we go. I don't want these orbiting each other at all. Let's go ahead and just rename these now. So everything is now beyond 10. C114. $15. 16. 17. 18. And now I can save the simulation under test again. And we should be good to reload now. Okay, so now we are at C110, 111. Excel is your friend when building these type of systems. Having an outside document where you save all your information and then you just write some functions in Excel. Learn how to write functions and structure them well. That is key. Let the functions do the work for you. You can randomly generate certain things, but the functions will figure out what mass a thing needs to be. All you have to do is figure out, okay, what size in kilometers do I want this? And then what density in grams per cubic centimeter do I want this? Once you have those numbers, just write some formulas and it will tell you what to input for all your mass values. And then you just have to move these sliders around until you get your density. That is if you want to match the sizes you put down on paper. I'm just a little bit meticulous about this. I don't think that this is adding anything particularly intriguing about my system. It's just some busy work, I guess. Didn't mean to zoom in on it, but now that one is the correct size. Ooh, that one's like 24.8 kilometers. I guess I did allow some larger minor moons in this moon system. Sometimes you forget what you've done on paper. Let's go ahead and move on to C12. .49466 times 10 to the negative 9th. It's rounding more and more of the decimal places for the size, the size in terms of mass. Not really size, just should use the term mass. Okay. I don't think I've had any that are at 8 kilometers around. Not for these. 2.18 grams per cubic centimeter. There we go. And once we get done with all of these, we're going to put them into the proper orbits. And then we can worry about the next set of moons for this moon system. C113. .22857 times 10 to the negative 9th. And this one is below 2 grams per cubic centimeter. Need to be at 1.94. And why am I going so low? 1.94. There we go. That makes sense. 14 kilometers sounds about right for those dimensions. And we are moving on. this one is a pretty big moon. And you know what? We don't really want a moon-sized, we want a pretty small asteroid-sized minor moon. All of these are captured objects around the gas giant that is the host planet, which is why they're minor moons and not major ones. The major ones would seem like they would be close to the equatorial plane of the planet, and that is what the major ones are currently built like. Sorry, I'm losing track of what I was doing. I'm trying to get to 2.26. Sometimes talking and doing is not my strong suit. There we go. That's what we want. And now we're on to the 15. C15. .18697. Too many decimal places, but who cares? Okay. Let's put this in grams per cubic centimeter and correct our value. We're wanting to get down to 2.12. Barely overshot it. And there we go. That's what we needed. We want to move on to 16. Okay, so going to edit this one to be 1.96575 times 10 to the negative 9. And that's under 10 kilometers. So I know that I don't have the right density yet. I mean, for 2.28, oh, I thought I like hit it perfect. 2.28. There we go. See how small it is? Now on to 17. We're 2 away from the end of the mass of updating the masses to be correct. Just trying to maneuver through my spreadsheet without accidentally double tapping the mouse. The Chromebook mousepad is not the type of mouse pad I prefer. Trackpad, whatever it's called. I don't like it, whatever it is. Okay, now that we are small and potato-like, we need to go down to 1.93. Add more iron and silicon back in. Come on. We just need to be at 1.93. Maybe if we go down and then back up. Yep, we can get there. Sometimes you change it, change one of the ones you think would update it correctly, and then move a different slider and it gets there perfectly. All right, we are on the last mass for C1 moons, progrades. That's what these are. These are the prograde moons. They're a little bit closer to the planet. .07215 times 10 to the negative 9. Yeah, prograde moons for these, I have changed the way I'm setting them up so that the prograde ones are a shell that's like a mid-tier shell. I have basically 4 levels of moons. You could say I have 3 levels of moons with the most inner, then the major moons, and then I have what are called the C-class moons. And I've kind of split the C-class moons into 2 levels. Your prograde moons, which usually for this, to keep them orbiting around the gas giant, I restrict myself to between 20 planetary radii from the planet. So you use the planet as your base of measurement. Between 20 planetary radii and half of the hill sphere. And I can go over how to calculate the hill sphere in a bit. Or you can look it up on Wikipedia. Let me see if I have a quick way to explain it. No, all my calculations, yeah, they don't have, I don't remember the equations off the top of my head. But it involves the mass of the satellite and the mass of the main planet that is the attractor, and you figure out how far out you can have a moon. Not the mass of the satellite isn't really taken into account. It's the mass of the planet, which is Kentage in this instance. So Kentage and Yantai, they are the 2 which is the star. Gonta is the star in this system, this custom system. So you would use a mathematical equation comparing those two masses with each other and how far away from each other they are, and you would figure out how far out you can have a moon on this planet that's gravitationally influenced primarily by this planet. If you have anything out beyond what is called the Hill sphere, the star is going to disrupt its orbit enough that it will just start orbiting the star rather than the planet. So that is what the Hill sphere is. Having your prograde moons orbit between 20 planetary radii and halfway into the Hill sphere. But I've even restricted it even more to make it between 20 planetary radii and a fourth of the Hill sphere. And then between a fourth of the Hill sphere and half of the Hill sphere, I have been placing what are called my retrograde moons, C2 moons. So my second group of moons. And because retrograde orbits can be stable at greater distances from a planet, I actually like to have them out further. And the person who I got a lot of this information of how to build these star systems sets it up this way. The retrograde moons are usually more distant, but technically they can orbit anywhere between 20 planetary radii and the edge of the Hill sphere. So you could have your retrograde moons and prograde moons just be thoroughly mixed throughout, but it might not be as realistic. Okay, where was I with 18? I don't think I had adjusted. I hadn't adjusted the density to match what I have, and that needs to come down to 2.24. There we go. Now I am going to save. I really don't want to go through entering all of those mass and density numbers all over again. So now that we've saved, I'm going to pull up within the same spreadsheet, I have a list of the orbital characteristics that are important for these. So C1, orbital characteristics. This is going to be orbiting at 18.038611 kilometers. And it's going to have an eccentricity, which is how elliptical the orbit is. The more eccentric an orbit is, the more it's going to be shaped like a flattened circle. If it's close to 0, it's going to be a pretty normal circle. Uh-oh. Accidentally hit something wrong for. I must have hit something definitely wrong in my calculations here. Well, the hill sphere is rather large for this planet, but I didn't think. I was looking at the first C2 moon instead of the first C1 moon, and I entered the wrong value. I knew it shouldn't be so far away. And this one is still pretty far away. And this is the closest of the C1 moons. And it's still 0.22 eccentricity. Now for these moons, I chose eccentricities randomly between an eccentricity of 10 and 30 degrees. Or not degrees. 0.1 and 0.3 eccentricity. I can't talk today with what I'm meaning to say. And then I chose values for inclination between 30 and 40. Sorry about that crack there. Okay, back on track, hopefully. This inclination needs to be 32.35. And these two values are going to open up these two values. Now that those values aren't 0, I can edit these two. 351.69. The inclination is how much the orbit is tilted, and the argument of periapsis rotates the entire thing along. Where the moon is going to be closest to the primary body that it's orbiting, that gets rotated along when you move this degree value. And this can, if you're just wanting to create randomized orbits, you can restrict certain values and randomize others. And you can definitely randomize the argument of periapsis for this type of a moon to just get pretty even distributions. And then the right ascension of the ascending node is another one I randomized for this. And of course, your starting position when you're at t equals 0. I don't have enough room on my spreadsheet for all the data I want viewable at the same time. I randomize something called the true anomaly on my spreadsheet, and I use the true anomaly to calculate what the mean anomaly is. So if you're wanting to take a shortcut, you can just randomize the mean anomaly between 0 and 360 degrees. And this just is a starting position within its orbit. Let's look. Okay, it's not going to let us see the actual orbit it will take. And that's okay. We'll figure out what it looks like another time. And then, of course, like most moons around these gas giants, I'm just going to tidally lock them to the gas giant when I create them right off the bat. Okay, so here we go. The next moon. This one is at 1,424,734 kilometers away. And the eccentricity is at 0.114. Still pretty eccentric, but not super so. All right. I'm trying to figure out how I can organize my spreadsheet here to make it easier to view a few things. But I don't think I can just hide columns like I could in Excel. I can. Okay, that is good. I was worried I couldn't hide columns. Bear with me. I am currently hiding some columns so that I can get back into this and see everything that I need to see. Okay, I have everything I need to streamline this, hopefully, in one page on Google Sheets. Okay, so inclination, it's not 0, it is 3, 8. Argument of apoapsis, or argument of periapsis, not apo. 343.82. And then our RAAN is 68.29. And then we have a calculated mean anomaly here. I'm entering the wrong values for a few things here. This needs to be 19.39. Then our calculated mean anomaly is 35.5. Okay, so I am going to do the rest of this dirty work of adjusting the orbital statistics for this off screen. I am a little bit tired, so I think I'm going to take a break from this. And go ahead and go to bed. I might put the stream back up for everybody to watch Dedunked just have its moon circle around it like I usually do. So please go ahead and subscribe if you like my content. I plan to eventually release an actual video detailing the process of building a moon system, the specifics on what you need to do, like the resources I use, the videos I reference. I can go ahead and put that together, but I'm not going to guarantee it will come out in any timely manner. I have real life that takes up a lot of stuff, and not trying to whine here, just reality calls sometimes, and I can't do YouTube full time right now. So please like, subscribe, and join me, Time Mao, for more videos, Universe Sandbox and otherwise. And we'll see you another day. Bye-bye.